Hi, my name is Billy Jackson, and I'll be recording this lecture on probability. I'm recording this lecture for my Honors Statistics course at North Shore Community College, and this chapter comes from the OpenIntro Statistics textbook. This lecture will be a demonstration of topics in probability using R and RStudio. While there's a lot of reading in this lecture, I will be using this video to only go over the examples, and any of the viewers can press pause at any time during the video and do the reading themselves. And I will only be reading explicit definitions when I feel there's a need to elaborate. So as you can see, open up right here is the knitted version of an R Markdown document. I'll be going back and forth between this knitted version and the R Markdown file version in R when I want to make some changes. So here are some learning objectives. You can read these on your own: defining probability, event, sample space, and probability distribution, calculating the expected value of a probability distribution, calculating conditional probabilities, calculating probabilities of one of several events occurring, calculating probabilities of several events occurring in sequence, and also, I didn't include here, also we'll be calculating probabilities of at least one event occurring. So you can read this next chapter below, and also you'll see me in this in the R Markdown file. You'll see me use a lot of a popular math typesetting system called LaTeX, which is used by wrapping dollar signs around certain functions, which produce nice looking knitted output, which you'll see throughout the document. So in this lecture, you'll see us use a couple examples to illustrate some probability concepts. One is a standard deck of playing cards, which you can familiarize yourself below. And the other is the game of American Roulette, which you can familiarize yourself with the reading and picture below. Alright, so what is probability? A couple definitions here. Probability relates to some kind of procedure. An event is a result of this procedure, and a sample space for a procedure is the set of all the possible events. So for example, let's suppose I flip a coin 3 times, and I'm interested in how many times the coin landed heads up. There's a variety of possible outcomes in this procedure, which we call events. All those events make up the sample space. So what is the sample space for this procedure? So let's write down all the possible outcomes in this sample space in our R Markdown file. So I'm going to go down to line 55. So there are some ways to create a sample space. One nice way is called a tree diagram, which you can look up on your own. And when you create a tree diagram, you find out that all the possible outcomes for flipping a coin 3 times are heads, heads, heads. They could all end up heads. The first 2 could be heads, and the second one tails. Then you could have a heads, then a tails, then a heads. Or a heads, then a tails, then a tails. Or you could have tails, tails, tails. Or you could have tails, heads, tails. Or tails, heads, heads. Or tails, tails, heads. And that is all of them. Those are all the possible outcomes. So there are 8 total outcomes. Probability, I'll go back to my R Markdown file, or my knitted file. Probability is the likelihood of an event occurring. The probability of some event occurring generally boils down to some version of a formula that looks something like this. The probability of some event E occurring is the number of outcomes that could satisfy event E divided by the total number of outcomes in your sample space. So then we can organize all this into what's called a probability distribution, which is a table that shows the probabilities for all the possible outcomes for that procedure. So the probability distribution for how many heads come up when flipping a coin 3 times is, we're going to fill in this table here. So all the possible outcomes when you flip a coin 3 times, you could get no heads, you could get, which would be all tails, you could get 1 heads, you could get 2 heads, or you could get all 3 of them heads. You can't get a value like 2.5 heads. You can't get 4 heads. You couldn't get -1 heads. So these are all the possible values. And we're going to find out the probabilities of all of those. So if we look back at our sample space, and you'll see here some of that LaTeX format that generated this nice looking formula. And this is some nice R Markdown language that can create that table that you saw on our knitted document. So let's fill this in with the probabilities. What is the probability of getting 0 heads? Well, how many events in our sample space had 0 heads in them? As you can see, just 1. So there was 1 event that had 0 heads out of a total of 8 possible outcomes, so the probability is 1 out of 8. How many of these outcomes have 1 heads in them? Exactly 1 heads. I see 1 here, HTT, a second one, THT, and a third one, TTH. So that means 3 of them out of 8. So the probability is 3 divided by 8. You can continue this with 2 heads. You'll see 3 outcomes in here, the HTT, THT, HHT, HTH, and THH. Those are the 3 outcomes that have 2 heads in them. So 3 out of 8 outcomes. And then there's just 1 outcome, the one that has all heads. Oops. That has 3 outcomes. And we can knit this back to an HTML. And you'll see my table has been filled in with the corresponding probabilities, and that's a probability distribution. Now let's calculate some probabilities related to the game of American Roulette in R. So going into my R Markdown file, I want to find the probability of the ball landing on the number 12. Well, there's only one number 12 on the roulette wheel, and there are 38 possible slots if you look back at the picture of the wheel. So the probability is 1 out of 38. What's the probability of the ball landing on an odd number? Well, the roulette wheel has the numbers 0 and 00, which aren't considered to be odd nor even. And then there's the numbers 1 through 36. How many odd numbers are there in the numbers 1 through 36? Well, half of them are odd, half of them are even, and half of 36 is 18. So the probability is 18 out of 38. What's the probability of a ball landing on an even number? Well, like I said, something that can often be confused is 0 and 00 are not considered even on a roulette wheel. So just half of the numbers 1 through 36 are even, which would be 18. So 18 out of 38 possible numbers are considered even, and that's the probability. What's the probability of the ball landing on a red number? You might have to look back at the picture of the roulette wheel for this, but it turns out there are 18 red numbers. So the probability of landing on a red is 18 out of 38. And what's the probability of the ball landing on a green number? Well, there are 2 greens on the wheel out of 38 numbers, so 2 out of 38. We could run all this, execute all this, and get all of our probabilities. I tend to like this argument in here, collapse equals true, which when you knit the document, it produces this nice output all right alongside all of the calculations. Oops, that didn't work. I must have a chunk option not set properly here. Let me fix that. Yeah. Here we go. Now that should knit just fine. Unless there's an issue somewhere else. So let's knit that. Here we go. So now you can see the comment describing the probability, and its corresponding decimal probability. Next, we have some definitions and terminology that are important for the following sections. So 2 events are considered independent if the probability of one event occurring does not affect the probability of the second event occurring. So some examples. If I flip a coin, what is the probability that it will land heads? Well, 1 out of 5, or 1 out of 2, 50%. Now if you flip a second coin, has the probability of getting heads or tails changed on the second coin? No, it has not. So therefore, these two events are considered independent. Now another case is, suppose you're dealt 2 playing cards in a card game. I get my first card and take a look. What is the probability that that card is an ace? Well, that probability is 4 out of 52, because there are 4 aces out of 52 total cards. Now a second card is dealt to me, and I'm still holding on to that first card. Has the probability of getting an ace changed? Well, yes, it has, because there are no longer 4 aces in the deck, and there are not 52 cards in the deck anymore. Right now, there's only 51 cards, and there's only 3 aces left. So the probability of getting another ace is 3 out of 51. So, and if I did not get an ace on the first card, then there would still be 4 aces left, so the probability would be 4 out of 51. So my probability of getting ace on the second card depends on whether I got the ace on the first card or not. So that would be called dependent events. Another definition is called events being disjoint. So 2 events are considered disjoint if there must be a typo in there, if the 2 events cannot occur in a single outcome. So another common phrase to describe disjoint events is mutually exclusive. So some examples. Event A is drawing a king in a deck of cards. Event B is drawing a queen. These are disjoint because there's no card that is a queen and a king at the same time. Now on the other hand, if event A is drawing a king and event B is drawing a diamond, these events are not disjoint because you can draw a single card that is both a king and a diamond. The next definition is complementary events. 2 events are considered complements if they have no overlap and they make up an entire sample space. So an example of complementary events, event A, students wearing a hat, B, students not wearing a hat. There are no other outcomes. Either a student has to fall into one of these categories. But not complementary events would be students wearing a baseball cap or students wearing a winter hat. This does not cover the entire sample space. There are many possible things that there are many other possible things that could be true. For example, students could not be wearing any hat, or they could be wearing a different kind of hat. Okay, now that we've covered a bunch of definitions, now we can get into some more examples. So the first thing we're going to talk about is something called expected value. For example, if you repeated many times the experiment of flipping a coin 3 times and recording the number of heads, what would you expect the average number of heads to be? If you think about that, you'd probably come up with about 1.5, because you'd expect it to come up half of the time, 50% of the time. So that is called the expected value of a probability distribution, and the probability of the expected value of a probability distribution is given by this formula here. It's given by the sum of all of your outcomes times their corresponding probabilities. So you find all these products of each outcome value times its probability, and then you take the sum of all of those products. Let's do an example in our studio. So we're going to continue with this example of what the average number of heads to be in 3 flips of a coin. So our x value for 3 flips of a coin was the values 0, 1, 2, and 3. So I'm going to store them into a vector called x. Then we need to come up with the probabilities. I'll call this vector px. And we already saw those probabilities. We came up with them. One of them is 1/8. The other is 3/8. The one for 2 was 3/8. And the one for getting 3 heads was 1/8. Now I need to come up with I need to multiply my x's times their corresponding p of x's. So we can do that. We can call this a new, or we could not even store it. We can just write x times px. And let's do all these one at a time. So you'll see I have some old stuff in my environment. I can actually wipe that out. Okay. So I'm going to store x in my environment. Then I store p of x in my environment. Then I find all of my x times p of x values, which you see are given down here in the console. And then you find the sum of those x times p of x's. and you see a value of 1.5, which is exactly what we thought we would get. So that's how to find expected value. So in the game of roulette, you can place a bet on the ball to end up on a black number. You can look back at the roulette wheel to get a sense of what that means. So let's suppose you wager $20 on this. If the ball ends up on a black number, you win $20. If it does not end up on black, you lose $20. So what is the expected value of your wager? So I'm going to go back into our studio. So in order to do an expected value, we need a couple things. We need x's, which are all the possible outcomes, numerical outcomes. And then we need probabilities of each of those outcomes. Then after we do that, we're going to multiply our x times our p of x's. And then we're going to find the sum of those x times p of x's. So what are the possible outcomes of this wagering $20 on black? Well, you could lose $20, which would be represented by negative 20, or you could win $20, which would be a positive 20. What are the probabilities of those occurring? Well, what's the probability of losing this? Well, how many of the possible numbers on the roulette wheel are not black? Well, 18 of them are black, and there are 38 total slots on the wheel, so therefore 20 of them are not black. So the probability of losing this is 20 out of 38. And the probability of winning is 18 out of 38. So I know I've used the same labels here for my vectors, x and p of x, but we can just run these, which will overwrite our old vectors. So we have new values of x and p of x. Here are x times p of x's, and we take the sum of them, we get negative 1.05. So therefore, the expected value of a $20 wager on black in roulette is an expectation to lose $1.05 on average. And I'm going to put some slashes in front of these dollar signs to make sure it doesn't think there's a formula inside of there. And that should probably make some sense practically speaking. A casino is not in the business of handing out money for free, so you expect when you go into a casino that the casino has an edge. And in this case, they expect, now in reality, you're either going to win 20 or lose 20, but if you do this many, many times, you're expected on average to lose $1.05. Or the casino is expected to gain $1.05 from every $20 wager. All right, let's do another example. In this example, Andy is always looking for ways to make money fast. Lately, he has been trying to make money by gambling. Here is the game he's considered playing. The game costs $2 to play. He draws a card from the deck. If he gets a number card, 2, 3, 4, 5, 6, 7, 8, 9, 10, he wins nothing. For any face card, Jack, Queen, or King, he wins $3. For any ace, he wins $5. And he wins an extra $20 if he draws the ace of clubs. So in this case, first, let's list out all the possible different cards that he could win with. So here I've created a vector for you. The cards are 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, and the ace we need to split up because he wins $5 for an ace, but an extra 20 if it's the ace of clubs. So I split that into two categories, and we can store that into our environment. Now let's list the winnings, the numeric values associated with each card. I'm going to store those into a vector called winnings. Now for all of the cards 2 through 10, they all have a value of negative 2. You don't win anything, so you just lose the $2 that you put up. So you'll see in this winnings vector, I repeat the value negative 2 9 times each of those for each of those cards. Then for Jack, Queen, and King, you'd win $1, $1, or $1. Why $1? Because you paid $2 to play, and you win $3, so the overall outcome is a $1 positive. If you draw an ace, you're going to win $5. So for ace other, I put a $3 net outcome because you paid $2 to play and you win 5, so that's a net outcome of 3. and you win an extra $20 if he draws the ace of clubs. So that's a total of $25 for drawing the ace of clubs, but you paid $2 to play, so the total is $23. So I'm going to store this vector winnings into our environment. Now let's list the probabilities of each of those cards. The cards 2 through king all have 4 of them in the deck, so they all have a probability of 4 out of 52. So I repeat the probability 4 out of 52 12 times. The probability of getting a non-clubs, that's an ace, is 3 out of 52, and the probability of getting an ace of clubs is 1 out of 52. So I'll store these into a vector called probs. Now I'm going to combine all of these into a data frame. I'll call this data frame Andy. And I'm going to use the data.frame function, and I'm going to bring in here cards, winnings, and probs. And we can take a look at what Andy looks like. So here you see the cards that he could pull, what his overall outcome would be. Winnings is maybe not the best choice of word, but the overall outcome, and the probability of getting each card. So now what we're going to do is we're going to find the value of our x times our p of x's. The x's are the winnings, and the p of x's are the probs. So find the product of Andy winnings times Andy probs. So this will give us a vector of those products. And I can even attach this into the data frame by giving it a new variable name. So let's say Andy xpx. And I'll store that as the product of these two columns. So now if I go look at the Andy data frame, I've got this new column, which is the product of all of my individual winnings and probability values. Now I'm going to find the sum of that column, which is sum Andy xpx, and that gives me Andy's expected value for playing this game. So Andy's expected value is on average to lose approximately 54 cents per play. Okay, feel free to pause the video and take a break anytime if you need, but right now we're going to move into conditional probability. So an example for motivation here is if a number came up red in roulette, what is the probability that that number was odd? I'm going to go back to my knitted version of this report, conditional probability. So here you'll see a formula that talks about conditional probability. The idea here is we want to first assume the number came up red, and then that is basically our new sample space. So the sample space is all the red numbers, and we're trying to find out how many of those red numbers were odd. So if we go back up to our drawing, how many red numbers are there? Well, 18 of them. And then you could go ahead and count how many odd numbers there are in here. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I count 10. So 10 out of the 18 red numbers are odd. So I'll go back into our studio. And so the probability is 10 out of 18, which is about 0.55. So that's an example of conditional probability. Basically, the idea is you have some condition which restricts your sample space. Now let's move on to the probability of one of a few events occurring. So an example for motivation is, what is the probability of a roulette ball landing on a 0 or a double 0? So in order to do this, we just add the two probabilities together. So the probability of landing on a 0 or double 0 is the probability of getting a 0, which is 1 out of 38, plus the probability of getting a double 0, which is also 1 out of 38. And that is just going to be 2 out of 38. However, if those two events are not disjoint, that probability is slightly different. Let's consider that formula above, which is that you just add the two probabilities together, and try it with this example. Use the formula above to determine the probability of getting a king or a diamond. So by that formula above, if you just added the probability of getting a king, 4 out of 52, plus the probability of getting a diamond, which is 13 out of 52, you would get 17 out of 52, which is, I'll write that here too, which is about 0.3269. Now, in actuality, that's not true. Let's go back up to our cards. A king or a diamond. Well, how many cards in this picture are either a king or a diamond? Well, we see on the right we have 1, 2, 3, 4 kings. And if we continue counting along our diamonds, we had 4 total cards so far. Now we have 5 starting at the queen, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we only have 16 total cards going down to line 214. Oops, actually 220. We had 16 cards out of 52 that were a king or a diamond. So a different probability. And maybe you can see here the issue is this thing called overlap. We had this one card that was a king and a diamond, which got double counted when we used that simple formula of just adding the two probabilities. And you don't want to consider the same card twice. So there's a way to correct this, which is just to simply subtract the overlap in our formula. And that looks like this. The probability of getting event A or B is given by the probability of A plus the probability of B minus the probability of the overlap. So we could change our formula up here in line 214. We add the probability of getting a king plus the probability of a diamond, and then we minus the probability of the overlap, which is the king of diamonds, which is a probability of 1 out of 52. And that gives us 16 out of 52, which we know to be the correct answer. All right, moving along. Probability of multiple events occurring in sequence. So an example, what is the probability of hitting a 0 in roulette and then rolling another 0 in the spin right after? So the way we find this is the probability of getting event A and event B is the probability of A times the probability of B. So the probability of getting 2 zeros on consecutive rolls, well, the probability of the first one is 1 out of 38. I'll put this in parentheses. Multiplied by the probability of getting a 0 on the next roll, which is also going to be 1 out of 38. So as you can see, the probability of getting 2 zeros on consecutive rolls is very unlikely, and that is found by multiplying the two probabilities. However, this only works if the two events are disjoint. If the two events are not disjoint, then the probability of event B, the second event, depends on whether A occurred or not. So in that case, we have the better multiplication rule of probability, which is the probability of A and B occurring in sequence is the probability of A occurring times the probability of B occurring given that A occurred. So let's do this out with an example. What's the probability, an example that we've seen earlier today, what's the probability of getting 2 aces dealt when dealt 2 random cards from a single deck? So what's the probability of event A occurring, which is getting that first ace? It's 4 out of 52. Then we're going to multiply it by getting the probability of an ace on your second card. Well, if you already have one ace in your hand, then how many aces are left in the deck? 3. And how many cards are left in the deck? 51. So the probability of getting ace on that second card is 3 out of 51. And you multiply these two to get the probability of 2 aces when dealt 2 random cards from a deck. Our last example we'll talk about today is the probability of at least one event occurring. This is a type of probability I'm particularly fond of because I've definitely thought at times while playing poker of this example I wrote for motivation. So in this example, I'm playing poker and I have 5 cards, 4 of which are diamonds. I get 2 more cards and I need 1 more diamond to complete a flush, which is when you have 5 cards that are all the same suit. So what is the probability that I'll get the flush? Well, the issue that complicates this a little bit is that there are a lot of situations here that could be in my favor. One, the first card I get could be a diamond and the second one could not be. Or the first one could not be a diamond and the second one could be a diamond. Or both cards could be diamonds. So there's really 3 situations here that would play into my favor. And in general, these probabilities of at least one, or one or more being satisfying what you want, these situations can have even more possibilities than just this simple one. And generally speaking, the probability of at least one is best interpreted as 1 minus its complement. So instead of thinking about, well, what's the probability that I get 1 diamond or 2 diamonds, the best way to think of it is, what's the probability that I don't get any diamonds? What's the probability that the one situation occurs which would be bad for me, and all the other situations would be good for me? So what I'm going to find out is, first, in this overall goal of getting at least 1 diamond in the next 2 cards, first find the probability of no diamonds. And then after that, the probability of at least 1 diamond is the complement of no diamonds. So the probability of getting no diamonds, that would mean I get 2 cards in sequence and they are both not diamond. So let's think about this probability. Maybe I'll have to write some stuff down here so far. So far, I have 5 cards. I have 4 diamonds and 1 non-diamond. So how many cards are left? So there must be 47 cards left in the deck. How many of those must be diamonds? Well, there were 13, and I have 4 of them, so that means there are 9 diamonds left. And how many non-diamonds are left? Well, if there are 47 cards left and 9 diamonds, then there are 38 non-diamonds left. So what's the probability of getting both cards not diamond? Well, on the first card, the probability of it being not a diamond is 38 out of 47. And then, I don't want to get this, but if I'm looking at the probability of getting not a diamond on the second card as well, let's assume that I've got a not diamond on the first one, which means now there are 37 not diamonds left out of 46 cards. So this is the probability of getting 2 cards in a row that are both not diamond, which would be a bad outcome for me. So what's the probability? Again, this is the situation that I would lose, right? I would not get the flush. So what's the probability of me getting the flush? It's the complement of that. So I can copy this here, and I can say 1 minus that probability above. So therefore, the probability of me getting the flush is about 0.35. So that covers this video lecture on probability. Hope this was helpful, and feel free to leave any comments below.